Hi, I'm Paul Kassabian, I'm a structural engineer, and the Gateshead Millennium Bridge was carried upriver by what at the time was the world's largest inshore floating crane. It was a 1,200-ton bridge and it was placed in one day. I was lucky enough to work at the steel fabrication and erection firm for that project for the whole year before that single day, only on this project. This video I want to share an introduction to what the Gateshead Millennium Bridge was as a design, which was spectacular in its own right, and also a lot of detail and images and video on the bridge fabrication and erection. It is truly an amazing project. I'm honored to have been part of it. It was a really fundamental part of my career, and I hope you enjoy this. So here's the design competition winning image of the Gateshead Millennium Bridge. A nighttime shot, because back in the 90s, that's what a lot of the images were. You'll immediately see the arch bridge coming across and spanning, while also having this complementary curved deck. And the cables that are going straight from the arch to the deck, so this is a cable-stayed bridge, are going from one side of the arch and going to one side of the deck. So there's a lot going on here. Also, along the bottom, you'll see some images of how the bridge rotates such that it can open. And I'll show you a couple more images about that later. So let's talk a bit about what's going on with the arch. So as I've used as a diagram in my previous arch video, we have the arch in compression. It's generally a parabolic shape such that it can be a sort of minimal section as possible. And importantly, arches thrust outward, right? You'll see that with the hands that I've got shown here. So not only is the arch being held up, it's also being held in at the ends to prevent it pushing outwards and prevent it splaying out. It always pushes out. And another thing that's going on, because the cables are going to one side, the arch is also in torsion. And so here is a section of the arch. You're going to see plate around the perimeter and stiffening as well. And so this is essentially acting like a tube. Remember, I did a video on torsion and tubes. Tubes are really good at carrying torsion because the material is consistent all the way around the centroid. And it doesn't have to be circular. It can be any shape as long as you've got material going all the way around. And so here's what you're seeing from that previous drawing of the material plate around the perimeter. These are different sections of the arch being welded together. Also, there's stiffeners that are stabilizing that perimeter plate. This is a stiffened box girder, is the phrase that's used. The same thing happens for the deck. This is the hollow tubular in form section, so perimeter plate. This is where people walk and the bicycles go on this cantilevered area, and the cable comes in from the inside of the curve. I know this looks empty, but here's a photograph of the deck being fabricated. It's actually upside down here because this part is flat. And so you'll see stiffeners running in both directions along the plate, and then also these sort of cross girder stiffeners as well. And if we do a close-up of where the cable comes in and look at the inside of this deck, you'll see there's a whole set of the stiffeners are sort of placed diagonally to carry the force localized from the cable that comes in from the outside, will be inside this stiffened cylinder and bear on this thickened plate from the underside. And you'll see an image of them stressing the cables later as well. So here's the top piece of 9 forming the arch. This 27 tons, that's just this piece. The whole arch weighs 350 tons. The whole bridge weighed 1,200 tons. And here's a lug that we use later on to pick up the whole arch. And so we're placing this bridge over the River Tyne. This is Gateshead, over here, the Gateshead Millennium Bridge. And one of the issues that comes up especially when you're dealing with an arched bridge, which is a situation where the arch only works when the arch is complete, right? And how do you place something like that over a river, especially when the river is an active river? This is the River Tyne. This isn't something that we could close for weeks or months on end. So a big problem was solving the issue of how to build this and place it. And luckily we found further to the east, which is the background of this photograph, a large layout area of land. And our plan, quite a bold plan, was to build the entire bridge, not just the arch or just the deck, the entire bridge on land, pick it up as one, and then place it. The advantage of being we can control this assembly and fabrication outside and take the time we need to get it right. And then we've also minimized the amount of time that the active river has to be closed while we're placing the bridge. So here's the arch being placed together and the bridge deck in its sections. And we rotated the arch upwards. It's rotated about these bearings at the end and placed it temporarily on this column support. Remember, with columns, you want to have area away from the middle. It's open lattice framework so that it's stabilizing itself as well. And remember this green square sectioned trussed object. We'll see it again later. So we placed it temporarily on this support because the cables are just hanging. We used this bearing that is going to get placed at the ends of the arch. You can see it in place here. And I wanted to explain that this goes at the bottom of each end of the arch. And that's what, when it goes to site, that's what it's pushed on by 3 hydraulic rams at either end. And they are the ones that rotate the whole bridge up. And when it comes back down, it actually rests, the deck rests, and it's stable by being supported on this bearing point and on a front bearing point as well. So there's 4 points of support when it normally is in its normal down position. And so here, remember we saw the inside of the deck when the cable was coming through. We've got the sagging cable because it's sagging under its own weight while they are tensioning up the cable to the deck. Remember the diagram I used in my cable video where whether you've got actual weights hung from a cable or it's just the cable self-weight itself, it will always drape to some extent. As you pull on the cable, it gets more and more straight. It will never actually be straight, given gravity and its own weight, but it may look quite straight to the eye. So here's the bridge in its essentially completed condition, sitting on land. So this let us build all of this in an easy way of accessibility. You can see the cables. They're a little hard to see, but they're going diagonally here. And notice, if you recognize, this is that big green truss part that we've added some ends on. And that's going to be the lifting beam to help us when we support from the big crane to a single point. And the cables from the crane are going to come down to either end and pick up this bridge. And so we need a lifting beam that's in compression so that we can keep the cables splayed outward, right? So we got to double use out of that piece of temporary works. And at one end of the bridge, just to give you a sense of scale, that's a person. I mean, he's crouched down, but still, that's a whole normal human being. And because we're on land and we've lifted the bridge and it's in its final state, remember I mentioned arches always want to push out. Well, we didn't have the ability to build something to push back on that on land. But we were on land, so what we did was we tied each end of the arch back to itself. That's what this cable is doing as a piece of temporary equipment. If you remember, tied arches are a way of connecting the bottom of each end of the arch to itself. And instead of pushing in, all you need to do is hold it up. Now it's sort of in a self-state of equilibrium, which is very beneficial if you're trying to pick something up. And this is how we picked it up. Here's the diagram of the crane, the very modestly titled Asian Hercules II. And we're picking it up. This is the single point that it's going to be picked up from because the bridge will have to be rotated. You'll see that so it can fit up the river. And then that's coming down to that square section that I showed you, the green long lifting beam, down to these points. And you'll also see a connection down here to the front, which I'll explain in a second here. So we did a lot of analysis in picking up this bridge. I know what you're seeing. This is after we did all analysis. But you know what? It's a really good idea to test out your plan for all of your stages of a pickup sequence and a landing sequence, that you're not missing anything. So to represent it with some very basic models, this is my ruler, a bolt, and all clipped together to sort of represent hanging this bridge from a single point. Okay, that doesn't seem particularly complicated, but the reality is that when we land the back of this bridge, this cable will go slack. And this cable wasn't just lifting up this end, it was also being balanced by this cable, which is inclined and carrying less weight, just the deck. And so if we land this bottom part only, and this cable goes slack, well, then nothing's balancing the horizontal part of this cable, right? So the whole thing would want to kick back. And you can do that with this little model, and it's no big deal. Little ruler and a bolt backs away. Well, you imagine a 1,200-ton bridge being lowered and then backing up into a whole bunch of people on site. That would be disastrous. So we planned to have this additional pickup point at the front just to be used for the landing so that we could stabilize it. And here we represent the landing on. So for some of you, this is what's called a camera film roll, where you took 24 photos. That's what you got, 24, or 36 if you really splurged and bought more. So this is our landing and stabilizing it on the front. So here we're ready on the pickup day. There's the actual crane coming into position, slack cables that are about to be taking up the load in tension and then balance off their horizontal component in compression in this lifting beam. And here we are coming up the river. Really fun story. The harbour master controls the River Tyne, and we very much needed him on our side because we were closing down the river for a bit and we needed to have various negotiations with him. So we had the good idea of asking him, hey, when this really impressive bridge and crane come up river, would you like to lead it in so that everyone sees you? And he was very chuffed by this. So we kind of won him over for that. And so here he is. That's him. That's the harbour master. So doot, doot, coming in, leading forward and for everyone to see the bridge. So it's turned lengthways on so that it could fit up this winding river. There's the green lifting spreader beam, and it's all hung from this single point. This is the last photograph I took for myself on the Gateshead side before I got into a little boat and went over to the Newcastle side, which is the side I was controlling. So it was quite an intimidating sight to see. So now we're going to move to a few images. These are by Graham Peacock, taken from a helicopter. So here it is arriving. This is Gateshead here on the left, the south side. This is the Baltic Flour Mills that became a modern art museum. Over here on the right, the north side of the River Tyne, is Newcastle. So Harbour Master's doubling back, and he's going to help rotate the bridge. Here it is rotating around into position, and now it's lined up. And this is a glorious photograph because you can see how the bridge is now joining a series of other bridges that cross over the River Tyne. Notice all of them are high. So tall boats come through, but there's a height limit as they come up the river. And so here it is coming into position. Another photograph of this. I think I'm either one of these people in a yellow jacket or somewhere over here at this time. Something that I hadn't really thought through, none of us. The Newcastle side was far busier because this was a public area, and the Gateshead side, this was a whole construction site. So while I was over here, it was quite interesting. When we got there in early morning, everyone was like, "This is amazing! You guys are great!" I was like, "Oh, thank you." And then 2 hours later, same people are you still here? And I was like, this is difficult. Okay, give us a moment. So here we are in position. Glorious photograph. As I said, it rotated, and you can see various videos of this online if you want to search up for it. And here it is in position, while there's lots of people who can be on it. And then when it rotates, it takes a few minutes, obviously, but it rotates and comes into position here. It's a really clever design solution, actually, because, as I said, you saw the higher bridges, so there is actually a height limit for the tall ships. And this is a really interesting way of moving the bridge out, so it doesn't have to open up or move out of the way. It's a really clever rotating idea by using two curved forms as an arch and a deck. I like this image because it looks like the people who were on it just got thrown off it. And it's got beautiful lighting design by Spears and Major. And that really adds, and a great photograph that shows it in context, very much a design and construction project of its day, very contemporary, using our sort of current technology and representative of what we're trying to achieve, joining the history of other impressive bridge design and construction projects from the past. If you want more details on this, we wrote a paper. I'll put a link to it in the description below. This is really an amazing project, and I hope you enjoyed hearing about it and learning some things about it too.